So we are going to continue. So since we have seen the particle character and how we could see this, how could have this interpretations of probabilities and in that sense. Now we are going to see how our understanding of waves is going to somehow sorry, it will take some time. So we are going to see how this wave interpretation, the wave interpretation. So we have been seeing. So we have seen in a particle interpretation the suitable choice of wave function on one side and eigenvalues on the suitable eigenvalues or the eigenvalues which the wave function or state takes in any direct or in some meaningful way how we can relate things. And once we could those eigenvalues, you can have numerical adjustments, or you can have they can correspond to some definite numerical values between two observers normally. Now we can have a definition which says so the value of entity u, the value of entity u measured in a situation measured in a situation u existing after measurement, before measurement. So the value of entity u, so its value, can you know its value or you don't know its value. So if its value is known, so before measurement and after measurement, and thus in a situation we can denote by S. U has all possible values simultaneously. U has all its possible values simultaneously. So for a given variable or an entity, if we have fixed its value, some value, so it's before or after measurement should not lead to any variation or discrepancy in our measurement. So for all times, its value should come out to be same. Now the question is, if it's a quantum mechanical state or psi, so for a given eigenstate operated upon by an operator or an eigenfunction which corresponds to a given eigenvalue, there may not be one eigenvalue. So different states can correspond to the same eigenvalue. So that's the point. And yes, that's the point. That's the point. Yes. And the other point is that there cannot be for a given eigenstate. It can have one unique eigenvalue, but it can have many eigenvalues. And those eigenvalues can be continuous as well as discrete, that we know previously also. So now the question is that so if there are continuum of values, our state psi, we take values in terms of as if you have some field is there. So in a sense, that's why we can say, technical sense, the mathematical reasons for that Schrodinger equation, or time-dependent Schrodinger equation can be grounded in a way where we assume that psi is additive. This means if we have two different possible descriptions of psi, that psi 1 and psi 2, we can interpret them via additivity of amplitudes, such that this will be sort of superposition. This corresponds to a sort of superposition in that sense. Now the point is, that if you have a particular interpretation, the superposition is then understand it. But for the wave thing, the wave interpretation, we had either or description. In wave thing, if you take it as a wave part thing, so once in that interference experiment, so there is either or thing which comes out to be once we have interpretation of those interference experiments. So before we are going with that, so for example, if we have, for example, psi1 q is a wave function, its f is operated upon, so you can have d1q or d, this is, we have done previously also. So you can have a psi1 function, which is operator, you can have operator of this form or derivative of that thing, or psi2 q can be related as f operator, you can have d2q or t by dt of dtq. So the superposition which we have denoted psi, you can write it as psi1 plus psi2. You can have psi1q plus psi2q. So dq psi is basically f of operating upon psi of q. So you can have two operators, this and this plus this. So either it will be for d1q, it will be d1q d by dt of d1q, comma, this one, psi1 plus so f of d by dt of this thing, d2q and d by dt of dtq. So this is one, and the other is for this operator d by dt. So you can add this and this, you will have d by dt of f operator psi of q can be f operator d1q d by dt of q d1q plus d2q d by dt of d2q. So the question is, so this is a simplest, this is how we can represent the superposition and how we can invoke operators in our understanding of this superposition, how operators can be added in that sense. So, but we have to basically if you remember, we described in the first chapter something called phenomena and something called interphenomena. In phenomena, you can simply explain things, but in interphenomena, the value of a given measurement of a given quantity or a variable is somewhat causally related to some another variable. We interpolate a given phenomena which is causally connected with that phenomena in some indirect way. So that's it. So in that sense, you can say either we can have probability interpretations if we have a particle way of things, or we can have, if we have a wave nature, we can, if the wave, once we have wave interpretation vis-a-vis those thought experiments, we have either or. Once something enters into this diaphragm, if there are two pinholes, so we have a interference pattern out here. So sometimes causality has to be somehow compromised if we want to see. The more we try to pin out the effect on the screen, the more it becomes less clear whether the contribution was from one pinhole or the other pinhole. So we had either or thing in that sense. So in the same sense, so you had interphenomena once. So in that sense, you have to see how you can interpret a Schrodinger equation, time-dependent Schrodinger equation, or psi vis-a-vis this thing, how the wave evolves. And if we have wave psi as a quantity, and psi square is the probability amplitude, the way we have for light. So if psi q, if psi q is, if psi q is, if psi q is, what I should say, if psi q is, psi is the probability amplitude, so you can have, so one of them can be k state, another can be m state. So we can represent one of the wave functions as sigma k psi k qt, another as sigma m star sin star qt. K can be equivalent to m or not. So if it's this way, so we can also have k and m greater than or equivalent to k. So we can have sigma k, sigma. So now again we can have psi, we can write psi m in terms of phi. So we can have those psi's can be written in terms of sigma ik into phi of ik. Some operators where sin phi can be related. So we can have sigma m, we can get it here, this can be here. Psi k we can write it in terms of sigmas, sigma m star, one of them, as phi m star e to the power minus iota 2 pi. If you remember our states, stationary states, once we had how this one of the expressions was there for this thing. So we can have this equation can be written in terms of sigma k star, phi k star, sigma m, phi m minus 2 pi iota by h m minus h k into t. So again, if you further would like to just, if it's a complex wave, we can write it in terms of cos and sine, minus sine will cancel, we will have cos and cos. So we can further simplify it such that a function of psi of q can be written as E naught is some constant plus sigma k m greater than k. So we can have one of them can be causes can be taken together. Am is a coefficient which includes all the things. Cos of 2 pi mu mt plus am sine of 2 pi mu mt. Where you can say nu m is basically nu m is hm minus hk by h. The same can be done for this thing also. And A0 as a constant can be written as for ortho states. It's sigma k square, it's sigma k square and sigma m square. where AKM can be sigma k, phi k, sigma m star, phi m star, where nu is the frequency of these two states. Not stationary states, it's basically one is the transitive states, the other is the stationary states. For stationary states, this may not be, it may be one, but for transitive states, so it's basically, we have done this thing. So it's basically how we can represent a wave function, how its evolution in a typical sense, how we can see its evolution in that sense. Now the point is that the duality of wave and corpuscular interpretation is sometimes presented as a parallel to the transformation of the state function. So in a sense, we sometimes say that discreteness should symbolize as if there is this corpuscular interpretation. Because there is also in the vocabulary of quantum mechanics some of the words crisscross or overlap, and sometimes they lead to misconceptions. Or their value may be approximate to what it intends to. So, because the idea of corpuscular and wave, these two ideas are enmeshed in a very subtle way in that sense. So, for example, so the Hamilton, the total value, the sum of the total amount of energy, the Hamiltonian can be written as Hamiltonian can be written as sigma k square. It's basically here where sigma. So sigma is this thing, hk. This represents the total value, but in the corpuscular interpretation, we had the average value. We normally talk of average value. But each wave function can have both interpretations, corpuscular as well. So if we have, for example, energy operator, H operator, which is split into sum of operators. This is H operator on state 1 plus H operator on state 2 plus, it's a sort of energy operator. So we are going to use Schrodinger's H side is equal to E side. So that will correspond to different states, eigenfunctions operating on operator, that will give different states, such that, for example, H operator operating on phi of km is HKM phi km. So now you can use the same interpretation in the sense this, you can have this hk is equal to this thing, or phi k can be represented as phi k1 k2 so on and is equal to phi k1 phi k2 so and h is h1 plus, these are different Hamiltonian states. This is total Hamiltonian, but these can be individual Hamiltonians. So you can see H operator operating on this phi function will give these states. You can have additivity can be there, H phi. So you can have H operating on phi of k is H operating on phi of k. This is one h operating on 2 phi of k plus so on h operating on phi of k. So it's equivalent to phi of k1, k2, kn, h operating on phi of k1, phi k1, phi k2, phi kn, h of operating phi k2 plus phi k1, phi kn minus 1, h operating on. So it's equivalent to, you can say it, h k1 plus you can have h kn and phi k1 and kn. Now we can consider, so we have written h in terms of phi. If you remember Schrodinger equation, h psi is equal to e psi. So you can write as this phi's. You can have psi's also. You can say it. So you can at the end write it in this way. So now we can consider psi as a wave function, and the psi k1 and different psi. It's dependent upon 20. Psi can be written as different psi's can be written as phi 1, phi 2, e to the power minus 2 pi by out over h. These are the different Hamiltonians, hk1 plus hk2 plus hkm. Psi that we can say psi of kmt. So here I'm writing. K1, Kn, sigma 1, sigma K1, sigma Kn, phi K1, phi Kn. So here we can have e to the power minus 2 pi over by h, hk1, hkn, t. And basically we have c psi of kn can be written as phi of km. So it's basically how we can have an operator operating on different states, and how in the Schrodinger equation it can be written as those additivity of those different states. And further, if we can have, if we represent psi, basically psi like this, psi and phi, psi like this is Hamiltonian. So these can be different Hamiltonian, h1, h2, h3, and so forth. So whereas you can say hk in the corpuscular interpretation maybe represents energy of the particle. So in the wave interpretation, this is equivalent to hk by h. So in corpuscular, so we can say how we can relate corpuscular and the wave. In corpuscular interpretation, psi q t square represents probability density thus determines the number of particles at a given place at a given time. While in the wave interpretation, it will it does mean as if we are seeing the intensity of the field. In corpuscular interpretation, we have something is localized. We have a particulate way of understanding things, or localized way of understanding things. So we can measure things, its number of particles which are, what I should say, traversing, relative number of particles in a given time. Or you can say, if you want to see it in terms of wave, you can see the intensity of wave in that sense. Psi square represents intensity of the wave. So so these conditions can similarly hold for not only for what I should say. This wave particle duality can also have the same sort of logic, can be incorporated in the way we try to see electromagnetic waves. Although there can be mathematical complications attached or associated with this thing. So there's one sentence which says that although corpuscular interpretation of light waves is analogous to the duality of interpretation existing for swarm of electrons. So corpuscular interpretation of light is analogous to the duality existing for swarm of electrons. Means a swarm of electrons or a bunch of electrons can have a behavior which can somehow be appreciated. The way we have an electronic gun, you can say it. You can the particulate nature can become pronounced if there are a bunch of electrons or many electrons. They hold themselves together, not individually but as swarm or as bees go together. Then only their effect can be just appreciable or observables. Important point is that the both, whether it's the wave character or whether it's the particulate character or in the duality interpretations. The way we have, so we can have either. One is the complementarity picture. You can have, if you want to have a complete description of wave in a given experimental setting, it will come at the cost. There will be less precision of measuring the other thing, the particulate thing. If the particulate thing is a more thing, more concentrated on the wave aspect becomes that indeterminate. And there was a particular interpretation in this book. We cannot have either or interpretation. We can not. We can have both interpretations. We cannot design an experiment. One is the exclusivity part. One parameter is the accuracy of one parameter is at the expense of another parameter. In an indirect way. If you increase accuracy of one, it comes at the cost of others. This is one thing. The other is that you cannot design an experiment where you can, if I remember, that interpretation was given by. You cannot. There is a third interpretation, if I remember. One was restrictive interpretation, the other was exhaustive. So leave away somewhere written that we cannot, in any given experiment, we cannot find, we cannot totally, I don't exactly remember. The interpretation, that interpretation is, the statement of that interpretation is not negative. Negative in the sense. It's not one thing at the expense of other. It's exhaustive. It takes both the things together. In the next class, I'll just start, if I remember, what was that statement. In today's class, it was merely how we can show how waves and particle interpretation can be just how we can see in that sense the phenomena and the interphenomena in the indirect sense and some calculations. So.